Hi, I'm Kohei Tokunaga from NTT. I'm mainly working in the container runtime and a maintainer of Stargz Snapshotter project, which is non-core sub-project of Containerd. Today, I'm gonna talk about speeding up container startup by lazy-pulling images. First of all, let's get through the summary of this talk. Pull is one of the time-consuming steps in container lifecycle. Stargz Snapshotter, non-core sub-project of Containerd, is trying to solve it by lazy-pulling images, leveraging Stargz image by Google. Further runtime optimization is also held with an extended version of Stargz, which is called eStargz. The diagram shows the container startup performance for three types of Python 3.7 images. It pulls the image from Docker Hub to EC2 Oregon and runs print hello world. Stargz formatted Python image with Stargz Snapshotter reduces the time to take for pull operation by Lazypull, but run takes longer than the legacy image. And eStargz formatted image mitigates the runtime performance drawback with the optimization, and we will discuss in more detail with the following slides. There are also other OCl-alternative image distribution strategies in container ecosystem, so I'll briefly introduce some of them in this talk. First of all, don't you think that pull is time-consuming? As you know, pull is one of the most primitive operation for containers. It's a very general workflow that we pull containers from registry, then unpack and run them on nodes. But unfortunately, a research showed that pulling packages account for 76% of container start time, but only 6.4% of that data is read. Of course, some workarounds though, but they are not enough actually. We can cache images on those, but the first time of the pull, called cold start, is still slow. And we can also try to minimize image size, but not all images are easily minimizable. Let's say we cannot avoid using some large base images, including language runtimes, frameworks, etc. Before taking a deeper look at the pull performance problem, let's briefly recap the OCI Docker specs for image distribution. In the specs, a container is defined as a set of layers. In image spec, it defines layers and metadata, and in metadata, image manifest, etc. are contained, and layer is defined as tar and optionally plus compression, and BruteFS can be composed by merging layers. In distribution spec, it defines HTTP API of registry, and layer can be fetched as a blob named with a content addressable digest. And registries optionally support HTTP range request, which enables us to fetch the partial ranges in a blob on the registry. And when it comes to pull performance, there is a problem on the current OCI Docker specs. A container is a set of turbo layers, so a container can be started until all layers become locally available, even if the most of the contents won't be used on container startup. As shown in the diagram, a layer blob is defined as a tarball, optionally plus compression. This means we need to scan the entire blob even for extracting single file entry. If the blob is gzip compressed, it's not seekable anymore, and we cannot extract it in parallel. So we need to scan the blob from the top sequentially. Because of them, we need to wait a long time for the pull and extraction completion on container startup. The Stargz Snapshotter is a non-quota project of Containerd. Containerd is a container runtime project in CNCF, which is also used by Docker. Stargz Snapshotter is a plugin for Containerd which provides Lazypull functionality for Containerd. And Lazypull here means Containerd doesn't download the entire image on pull operation, but fetches necessary chunks of contents on demand. It means we can start containers before the entire image contents being locally available, so we can speed up the container startup performance. Lazypull in Stargz Snapshotter leverages Stargz image by Google, which is standard compliant, so we can Lazypull images from standard container registries, including Docker Hub. Let's do the demo. First, I pull Python 3.7 image from Docker Hub and run print hello world in the container with Containerd in a very normal way. The image size is around 338 megabytes on the registry, so pull takes accordingly. We need to wait for pull long time, and if the image takes 1 GB or 2 GB or larger, we need to wait for longer and longer. Sometimes it's called cold start problem. In this case, the pull took about 32 seconds. Next, I lazily pull Stargz formatted Python image from Docker Hub. In this case, the pull took about 7.2 seconds. It's a Stargz formatted image but not squashed, no content is lost. This speeding up is the power of Lazypull. I'm pulling this image in Tokyo, and if you are in different locations, you should get different results. For example, in the benchmarking results in Oregon, which I will talk about later, the time to take for Lazypull is shorter. So how Lazypull is provided? Stargz Snapshotter leverages Stargz image, which is compatible to the current OCI Docker image specs, which means the Stargz image can be lazily pulled from standard registries, and it can also be run by legacy runtimes, but in this case not lazily pulled. In the following diagram, a registry is shown on the left side and a node is shown on the right side. On the node, Stargz Snapshotter is plugged into Containerd. For containers spawned by Containerd, Stargz Snapshotter mounts the container's root.fs snapshots as views. On mount, most of the layer contents are not downloaded yet. Instead, Stargz Snapshotter lazily downloads file contents accessed by containers on demand from the standard registry. Again, Stargz images are compliant to OCI Docker, so legacy runtimes also can pull and run it from registries. Again, but in this case not lazily. And Stargz Snapshotter itself is implemented as a remote snapshotter plugin. And remote snapshotter is a type of plugin of Containerd. Containerd allows remote snapshotters to remotely mount containers root.fs snapshots from remote store two containers on the node. So you can also implement your own remote snapshotter if you want to use remote stores other than registry. So what is Stargz? Stargz is an archive or compression format. It's proposed by Google CLFS project. Stargz stands for seekable Stargz, so it's seekable but still valid Stargz. So it's usable as a valid OCI Docker image layer. And entries can be extracted separately, so each entry can be fetched separately from registries using HTTP range request. Standard registries optionally, but I think most of registries support HTTP range request, so we can download blob contents per file entry on demand, which enables us lazy image pooling. As shown in the following diagram, the normal Stargz layer is non-seekable, and we need to scan the entire blob even for getting single entry. On the other hand, Stargz is actually the concatenation of gzip compressed file entries. This is still valid gzip, so we can decompress it in file or chunk granularity. And it contains an index called TOC at the tail of the Stargz blob, so we can get the offset information of each entry contained in the Stargz blob. TOC also contains metadata of all files stored in the Stargz archive, so we can mount this layer without seeing the header of each file. But network-related overheads can't be ignored for on-demand fetching with Stargz, especially on slow networking environment, because the read access to a file on Stargz induces downloading that file entry from the registry. eStargz enables to prefetch files that are likely accessed during runtime, and we call these files as prioritized files, and file system can prefetch and precache these files with a single HTTP range request or mount. So we can access these prioritized files locally. As shown in the diagram, eStargz allows to group file entries based on the priority. Let's say we know the files marked with red boundary is likely accessed, so prioritize files during runtime, and eStargz indicates this information about likely accessed files as the order of file entries. When Stargz Snapshotter mounts this layer, the files marked with red boundary are prefetched by a single HTTP range request and precached. Other files marked with green boundary, are also downloaded aggressively in the background. And leveraging eStargz, CLI converter by the project provides workload-based optimization. Generally, containers are built with purpose, and workloads are defined in the Docker file with the entry point, user, env, etc., and stored in the image. The CLI converter runs provided image in a sandboxed environment and profiles all file accesses, and it regards these accessed files are also likely accessed during runtime. So these files are prioritized files in the Stargz, and Stargz Snapshotter will prefetch and precache these files when mounts this eStargz image. As shown in the diagram, the original image is shown on the left side, and this contains workload information. So entry point, commands, user, etc. And the converter command runs this image in sandbox and profiles file accesses and generate eStargz. Again, when Stargz Snapshotter mounts this image, these accessed files are prefetched and precached, so we can access these files locally. And some benchmarking results with Stargz Snapshotter. It measures the container startup time, which includes pulling down image from Docker Hub, and for language containers, running print hello world program in the container. For server containers, it waits for the readiness, so it waits until up and running image message is printed from the container. This method is based on Hello Bench, and we took 95 percentile of 100 operations. And we used EC2 Oregon instance as the host and Docker Hub as the registry. And in Python 3.7, the time to take for pull Stargz is shorter than legacy images because containerd with Stargz Snapshotter only pulls image metadata and Stargz index files. But the run performance is slower than legacy. When we use eStargz on the other hand, runtime performance drawback is mitigated compared to Stargz. But the time to take for creating container is longer than Stargz because during the container creation, Stargz Snapshotter waits for the prefetch compression. In GCC 9.2.0, Lazypull also shortened the time to take for preoperation in both of Stargz and eStargz cases. For this image, run takes longer even with eStargz, and it is because the startup performance compiles Hello World C program, but the source code isn't included in the image, but provided at runtime by mounting the source code directory. Currently, the project's optimization command doesn't support mounting external directory, so workload optimization couldn't profile the file accesses during this workload. But this should be improved by adding volume functionality to the optimization command and enabling it to profile file accesses even with such runtime volumes. And for Glassfish 4.1, which is a server image, Lazypull also shortened the time to take for pull operation in both Stargz and eStargz cases. But Stargz takes longer for the server initialization, and eStargz image mitigates this. For eStargz image, again waiting for the prefetch completion during create occurs again. Pull operation is a fundamental operation in container lifecycle, so the performance improvement will be beneficial for many kinds of workloads. But I list some of them here. The first one is speeding up base image distribution on image build, especially for base image in dev stages in multi-stage build, because these images aren't included in the result image. The second one is speeding up dev pipeline or building testing environment. Stargz was invented through the discussion in Go community for speeding up the builder image distribution in their build system. The third one is sharing large scientific software stack, for example ML frameworks. ML frameworks tend to be large. They can be over than 1 gigabyte. And the final one in the list is improving cold start performance, for example in serverless environment. Of course, we need more investigation here for finding out what is the root bottleneck of cold start problem. But please be careful that Stargz Snapshotter project is still in early stage. It needs more performance improvement for the implementation, and Lazypull performance seems to be affected by the internet condition and instance location, etc. And also be careful for the fault tolerance until the layer contents are fully cached on nodes. And of course, feedbacks and suggestions for use cases and implementations, etc. are always welcome. There are also other OCl-alternative lazy image distribution in the community. I'll list some of them. First one is Stargz. It uses NFS infra for the distribution of Workload-based snapshots of containers, and registries are used for sharing snapshot IDs among hosts. And CERN-VMFS is a fused file system by CERN for sharing high-energy physics software on worldwide infrastructure. And software stack can be mounted and lazily downloaded from CERN-VMFS repository via HTTP. There is implementation of Containerd's remote snapshotter based on CERN-VMFS. Again, remote snapshotter is a plugin for Containerd like Stargz Snapshotter, but one can use any file system and store as backends. And there is an ongoing discussion towards integration of CERN-VMFS and Podman. And FileGrain is proposed by Akihiro Suda NTT. It is an OCI compliant image format, but uses continuity manifest as layers. An image can be mounted and files are pulled lazily. And each file is treated as a content addressable blob, so the application in file granularity is also in the scope. And there is an ongoing discussion towards OCI v2. It's proposed by Alexa Sarai Suze. OCI v2 is not official spec yet, but brainstorm is in progress. In the discussion, lazy fetch support and mountable file systems are also included. And finally, CRFS plugin for Fuse Overlay FS. It is proposed by Giuseppe Scrivano Red Hat. It is a plugin of Fuse Overlay FS for mounting Stargz layers. Finally, recap. A pull is one of the time-consuming steps in container lifecycle. Stargz Snapshotter Noka sub-project in Containerd is trying to solve it by lazy pulling images leveraging Stargz image by Google. It's standard compliant, so it can be pushed to and it can be lazily pulled from standard registries. And workload-based runtime optimization is also held with eStargz. There are also other OCl-alternative image distribution strategies in container ecosystem. And of course, feedbacks and suggestions are always welcome. You can access to our repo on github.com/containerd/stargz snapshotter. And thanks.